It will come when you least expect it. You've been warned. No. Yeah, let me take it out and give it to you now. No, not now. And not Monday. No. When you least expect it, when everybody feels safe and comfortable and they're not worried anymore, that's when the test comes. So, I have a look around and... What's that?
Later, after the class. It's the same joke as
Okay. Let's continue. So, we'll do the next lesson, and then in the next class we'll do the tutorial for both. So we're going to have a look at resistance now.
Are we going to short answers?
Yeah, in the next class we'll do both. I just want to make sure we get this topic finished today as a priority. We have 1 or 2 hours or no hours tomorrow. One physics hour. Okay, good. Resistance. You got that? So current, another definition of current is the rate of change of charge per unit time. Or as a formula, current is Q over T. Now, of course this makes sense because the formula in the last lesson was Q equals IT. So this is not a surprise, but it's just another way to define current. It's the rate of change of charge per unit time. Please don't poke your eye out with the pen, okay? Because if your eye falls out, then I have so much paperwork to fill out, and I don't like paperwork. Okay, you got that? Yeah. Now, this is a new term, voltage. It's like potential energy. It's a type of energy, nearly, a potential energy. So it's electric potential energy per unit charge. So what exactly does that mean? It's joules per coulomb. 1 volt is 1 joule of energy per 1 coulomb of charge. So what it means is, if this has 1 unit of charge, if I say it is at 10 volts, then that means for this unit of charge, there's 10 joules of potential energy in it. So voltage is like potential energy, but it's potential energy per coulomb of charge. Do you understand? So if this was 2 coulombs at 10 volts, how much potential energy is in here? 2 coulombs at 10 volts.
0.5.
No?
5.
No. Think first. 2 coulombs at 10 volts. What's the energy?
0.2.
No! 20 joules. Because 10 volts means 10 joules per coulomb. If I have 2 coulombs, then I have 20 joules. 10 each. Yes? Now it makes sense? I hope. Right. Resistance of an electrical conductor is a measure of the difficulty to pass a current through that conductor. The unit is the ohm. When 1 ohm, where 1 ohm of resistance means 1 volt of energy was converted into another form of energy. When 1 amp passes through the resistor. So I'll explain that in a bit more detail now in a moment. You got that? So what I'm saying is, 1 ohm means that 1 joule per coulomb was taken out and converted into some other type of energy, like heat, sound, something like this. Anything that uses the potential energy in the current is a resistor. We'll talk about this in more detail. But resistance just means a lot of the energy was changed. A high resistance means a lot of the energy was changed from the electrical to something else. Continue? Yes? Andrew? Continue? Yep. The following picture will help explain the relationship between current, voltage, and resistance. V, I, and or. Ta-da! So, ohm offers resistance. Yeah. So if the resistance is very big, then you'll need a lot of the. Remember, the voltage is the energy. Okay. So if the resistance is really big, will it require more energy from the voltage or less energy? More. Yeah, more. So if he is really big, this guy, more of his energy is taken and converted to push the current through the resistor. Yes? Oops. So, ohm resistance is very big. It means the voltage has to give a lot of its energy up to push the current through. So, usually a high resistance corresponds to a high energy conversion. A big resistor means a lot of electrical energy was converted into work.
So the voltage has to be bigger than the resistance?
No, not necessarily. It just means that if the resistance is big, probably a lot of energy was converted into work, electrical energy. Yeah. How can we measure voltage? We can measure voltage by using a voltmeter. And here's an old-fashioned voltmeter. This is how we can measure voltage. Now, it's extremely important that you understand that you can only measure voltage between 2 points. So you can look at the difference in the energy here and here. So for example, if there was some work done in the middle, then you can see the change in the voltage. You can know how much energy was converted into work. So you never put the voltmeter in the middle of the current. You put it around the current, like you clip it at two ends, and you measure it between the two ends. So you can only measure voltage between 2 points on the current. Okay, so voltmeter. How do you measure current? Using an ammeter to measure the amps. And this is what it looks like. This one you can put it in the middle, and it measures how much current in amps passes through it. So this one does go in the middle of the current. And lastly, do you want to have a guess? Yeah?
Doesn't it stay in the middle and then goes right and left?
No, that's a galvanometer. Galvanometer or galvanometer?
Galvanometer.
METER? It just measures the direction of the current, really. What does a galvanometer measure?
Just the direction?
Just the direction, I think. It just...
No, but it changes depending on the resistivity that you have, or the resistance that you have.
Possibly, depends on the circuit. What do you think measures resistance? Now, just to recap, to measure voltage is a voltmeter, current is an ammeter.
Resistor.
No, because what's the unit for resistance? Ohmmeter measures it. You measure resistance using an ohm meter because resistance is measured in ohms. Are you learning some English? Do you see how the word meter works here? How do you measure how annoying someone is? An annoying meter. You know? How do you measure how tired someone is? A tired meter. Get the idea? Okay. Continuing. You got those? And there's an ohm meter. Now, in fact, we do not use ohm meters on this course because they're extremely inaccurate. Voltmeters are good, ammeters are good, but ohm meters are extremely inaccurate. So we never use them in this course. Maybe more modern digital ones are better, but really it's difficult to measure the resistance using an ohm meter accurately. So we'll not study an ohm meter, but we will measure voltage using a voltmeter and measure current using an ammeter. An ammeter requires the current to flow through it. A voltmeter measures voltage between 2 points. Remember I said that earlier. In other words, voltmeters and voltages are always between points, whereas ammeters are always at a point. So if this is the current, the ammeter goes into the current. So the current goes in the ammeter and out the ammeter. Whereas the voltmeter, you like clip and clip 2 points on it, and the current doesn't go through the voltmeter. It's like the voltmeter looks at the current here and here. Okay? It's important you know that, and we'll talk more about that when we do circuits later. I've already explained it enough. Okay, so that's not how you spell triangle, but the following triangle will help explain the relationship between VI and OR. So there is a formula that relates VI and OR, and it's represented in this nice triangle. So if you want V, that's equal to I multiplied by OR. If you want OR, that's equal to V over I, and if you want I, V over OR. So the V or I triangle will let you calculate what's missing if you know two of them. It's worth writing this triangle down. Yeah. Seen this before? Probably. Continue. Right, let's have a look at an example. An ammeter measures a 250 milliamp current flowing through a resistor. The resistor is a light bulb. So if you think about it for a moment, we have the current, look, the current goes up and through the light bulb. The light bulb offers resistance to the current. So the voltage has to push the current through. And what happens? The energy is converted. In this case, what is it converted into? Heat and light. Yeah. So we know the current, we know the voltage, and I would like you to use the triangle to tell me what the resistance is by using the triangle. Calculate. So you have I and you have V. What's the OR? Got an answer? Yep. So what's the formula for OR? V over I. And in this case, what's the V? And what's the I? Yeah, 250 milli. So what did you get for the OR? 880 ohms. So I'd like again to state what that means. 880 ohms means for every coulomb that passes through, 880 joules of work is done per volt per coulomb. In other words, it's a lot. But let's forget about that. Next one. A 6-volt battery is used to power a toy which has resistance of 2 ohms. What's the current? Okay, so I think again you can do that using the triangle. What's the formula for I off the triangle? V over R. So it's 6 over 2, which is 3. If the toy is left on for 1 minute, how many electrodes flow from the battery into the toy? Okay, so we'll need to write that down. What formula could I use here?
I equals Q over T.
Q equals IT. Do we know the I? Yeah. Do we know the T? Yeah, what is it? 1 minute, so that's how many seconds? So that's 180 coulombs. But we want to know how many electrons there are, not how many coulombs there are. So how can I work out how many electrons are in 180 coulombs? Divided by the constant. 180 divided by, what number is the constant?
1.6.
23?
Yeah.
So it's this. So that comes out as a lot. 1.12 times 10 to the 21 electrons. No, because we want to know how many electrons, so we're counting. If the battery is replaced with a 12 volt battery, then how does the current change? Okay, so now we have V equals 12, I equals we don't know, and what does OR equal?
3.
Yeah, but the problem is the OR was 2. Yes?
Now it's 4.
Well, we don't know. We don't know how it changes. It was 2 previously, but we don't know what it'll be now. But what we can do is we can say, well, maybe it doesn't change too much, so we'll say it's roughly 2. The only thing we know for certain now is the voltage is 12. So the I is V over OR, which is 6. But it's not going to be exactly 6. You may assume the OR is constant. This is not always the case. And in fact, it's a law we'll see in the next class. The OR changes, just like the V and the I changes. Yeah, it depends on several things. In fact, even if the temperature changes in the room, the OR could change as well. So the OR is a variable like V and I. However, it's the one that changes the least, so sometimes we can assume it's a constant for the question. Yeah. Okay, that's good.
It's an exponential graph between R and temperature.
Yeah, but it's not always. It depends on so many things. For some situations it will be, and in some it will not. Okay, so again we have some pretty straightforward questions to do. If you can start them now, please. Guys, was there any trouble in the last exercise? Were any of the questions you couldn't do? The last one, maybe. And then what about in this exercise? Maybe not. I'm just thinking maybe in the next class, because these are straightforward, we'll just do the one that you found difficult.
Oh, we can do that right now. 20 minutes, 3 minutes.
Well, am I still recording? I am, okay. Sure, I might as well do the one that you found difficult in the last lesson. What one was that? If you can read it out to me.
I1 is a wire and I2 is another wire, then they join. What is that?
Parallel.
Parallel, yeah.
And they join.
And what's the current here?
Yeah, I1 plus I2. Yeah, what's the current here and what?
Yeah, so it's I1 plus I2 is the answer.
But why?
But why? Yeah.
Because
So remember, I is charge per second. So for let's imagine there's 2 coulombs per second here, because remember that's what amps is. If this is 2 amps, that means 2 coulombs a second. If this is 3 amps, that means 3 coulombs a second. If 2 people were walking down here per second, and 3 people were walking down here per second, then on this road you'll have 5 people moving per second. So when we have situations where currents come together, they simply add together. That's all.
How can we explain that? The question asked that.
No, that's not going to be an exam question. That's just make the student think about it question.
Oh.
Okay. How are these ones going? Which one are you on? Oh, good. Andrew, which one are you on? Great.
So the resistance can be bigger than the voltage sometimes?
It can be anything, yeah.
Or like proportional?
No, the relationship, the three numbers, they could be big, small, big, big. You're trying to think if one is big then the other is big or something like
What
that.
I'm thinking about is that the picture you showed us,
Yeah.
if the man is pulling with a stronger force
Yeah.
and the man pushing, then the man in the middle won't move.
Yeah, but the complication is if the orb is bigger, let's take the V is big. Sorry, the R is big and the V is big, but the I could be small. You know, and I suppose if the I was small enough, then maybe the V would be smaller. You know, it's
If the I was less than 1, maybe.
if the I was less than 1, then
Or it would be bigger.
the R would be bigger. Yeah. Finished? Let's do the answers together. Let's just see what you got. So, what was the resistance for the first one? 120 ohms. For the second one, what was the resistance? 110 ohms. For the third one, what is the current? What was it? 0.1 amps, or how many milliamps?
Amps. 100 milliamps.
100 milliamps. Part 4 now, what was the resistance of the mobile phone? 4.6253 ohms. So again, that means what is it? That's not that big. It means 4 joules per coulomb per second are being converted into energy for the phone, like, you know, the screen and the sound and all that. If the phone was replaced by a better, more powerful smartphone, but you kept the battery the same, do you expect the resistance to be larger or smaller? Now, who's this? Back already?
Yeah.
That was a quick doctor's appointment. Back already. Where did you go?
This is the doctor.
Where's the doctor?
With the traffic light.
And what did he say? Eat more chocolate? Eat less chocolate?
Eat more chocolate.
Good. That's always a good visit to the doctor. Okay, so what are we thinking about the last part here?
Larger resistance.
Larger resistance. Why?
Because the phone will use up more battery.
The phone needs to convert more joules per unit to power it. Because, you know, smartphones need a lot of power. So, if you just made the phone more powerful but kept the battery the same, then you should expect the resistance to go up, I think. But it gets a bit complicated because there's other things to consider, like the battery getting hot, you know, the battery maybe is underpowering the phone. It actually can get a bit complicated. But the point I want you to get is that things that use a lot of energy, like a smartphone, they have a big resistance. So if you think about your house, what items in your house would have a really large electrical resistance? Heaters, definitely. Television's not that high because it doesn't really convert much energy into heat. Anything that produces heat, toaster, kettle, oven, shower, these would have high, very high, like kilo ohms resistance. Things that have low resistance would be electronics, stuff like this.
What about air conditioner?
Air conditioner would be quite high, I think.
But it's cold, isn't it?
I know, but it's complicated. It's quite high because it has to do a lot of work to take the heat from the hot part of the room and to make it exit the room. It's quite difficult to do. Okay, so the good news is, Franz, we're just in time for the end of the class. Hey, what?
The result.
You saw them twice now.
But it makes me happy.
Maybe. Maybe not.
No.
What?
Why?
Everything was good with the doctor? No? Do you have to go back? Well, that's good. Did you have to pay? That's bad. Very, very bad. How much?
35.
35? Do you know how many chocolate bars you can buy for 35 euros?
I know a lot.
A lot?
I waste my money on the doctor.
Yes.
Nothing. He doesn't. I have.
And not only did you waste your money, but you also missed the physics class.
Yeah.
Which is probably worse.
That's why
Yes.
I can't go to the doctor.
Yes. Okay.